We are now going to go through the last two chapters in the book, chapters 5 and chapter 6. Now, I know this says section 4.9. Remember, I think 4.9 is better grouped with chapter 5 and chapter 6. We're going to talk about antiderivatives. Okay? Now, if you think of a derivative, I think of a derivative is going forward. If you have a function, you take a derivative, you go forward. Antiderivatives is just backwards then, okay? You're just undoing a derivative, okay? So if you know what the derivative is, can you undo it? Now, this introduces antiderivatives in 4.9, and then we're going to relate them to an important concept of finding areas, okay? Where's my eraser? Let's see, in chapter 5, we're going to learn how to undo the power rule. We're also going to learn how to undo the chain rule, okay? Now, when you take Calc 2, you're going to learn how to undo products, so like a product rule, and quotients. Quotient rule, you're going to go through more trig methods, okay? So this is just the basics of antiderivatives. It gets more detailed in Calc 2. So if we read that first definition, it says a function f, big F, is called an antiderivative of little f on an interval I, so whatever interval I we have, if big F prime of x is equal to little prime of x for all x in I, so all the x's in your interval. So what this is saying is f, big F of x is an antiderivative of little f of x if you take the derivative of big F of x, and whatever this function is, whatever differentiation rules you have to apply to it, maybe it's just the power rule, maybe you got to do the chain rule, product rule, quotient rule, logarithmic differentiation, anything, you take the derivative of this, and if you get little f of x, then you know big F of x is the antiderivative of little f of x. Okay? Alright, so let's look at an example. The first example I have is x squared. So we got little f of x equaling x squared. What we want to do is find the antiderivative of little f of x. We want to find big F of x such that big F of x, the derivative of big F of x is equal to little f of x. Okay, that's what we want to do. Now, if you know your derivatives really well, these will come easy to you, okay? If you look at it, this is the power rule. Like, think about if you were to take a derivative, you take the number up top, the exponent, you multiply it by the number out in front, and then you drop one power, okay? So if we were to do that to this function here, what does this function have to be so that we get this function? Okay, so if I think about how I would take a derivative, this is a power function, it's a squared function, so I should have a power function there as well. And if I were to take a derivative of this thing, and it's a power function, I know I'm going to have to drop one power. So instead of it being a squared, this should be a cubed. Because I'm thinking ahead. If I were to take a derivative of this, of course I'd have to multiply by the number out front with the exponent, but then I'd have to drop one power. That's how I got the squared. But now, I need a 1 out in front. if I think about how to take the derivative of a power rule, I take the number 3 and multiply it out front. So if I were to take 3 and multiply it out front, I would have a 3 here. But little f of x doesn't have a 3. It has a 1 right here. So I need a 1. So what number multiplied by 3 is going to give me 1? 1/3. Okay, so let's go ahead and check. Make sure that if we take the derivative of this, we do get back little f of x. Well, big F prime of x is equal to, just apply the power rule. The exponent times the number out in front, 3 times 1/3, x, and I'm going to drop 1 power. So 3 times 1/3 is a 1. 1 times x squared is just x squared, which this is equal to, it looks like a minus sign, is equal to little f of x. So this right here is the antiderivative of this little f of x. That is the idea of antiderivatives. We are going backwards, okay? If we have a starting function, can we think of another function so that if we take the derivative of this, we get back our original function? Okay, now there's a better definition, or it's actually a theorem. It says if big F is an antiderivative of little f on an interval I, so it starts out a lot like the definition above. It should say then the most general antiderivative of little f on I is big F of x plus c, where c is any constant. Okay? F of x plus c. All this is saying is that when we take the antiderivative, there is some missing information that was lost earlier when we take a derivative. So if we take the derivative of a constant, it goes away, it vanishes, it goes to 0. The derivative of a constant is 0. Okay, so if I have a function, little f of x, and then I anti-differentiate to big F of x, big F of x may have had some constant along with it, because then if I take the derivative, I still get back little f of x because the derivative of this is 0. Only thing is, if I start here and take the antiderivative, I don't know what the constant is, so I put a plus c on it. This is the most general form of an antiderivative. Big F of x plus c. Now, we can figure out the little c. We will see that in examples later if they specify some initial conditions. Okay? They have to tell you some point on here. So at x is equal to 5, big F of x is equal to 6. I don't know. I made that up. We'll see how to get values for this c later. So let's go ahead and redo our example that we just did. Okay, we had little. Oh, this blue's not working that well. Oops. Let's see this one. We had little f of x equals x squared. We came up with big F of x is equal to 1/3 x cubed, but we want the most general antiderivative, so I'm going to put a plus c right there. Okay? So when you find general antiderivatives, you have to put a plus c there. Now, what this plus c does is for a different value of c, you are going to get a different curve. You could have what's called a family of curves for different values of c. So, how this would look, now, if c is equal to 0, this just looks like a cubic function, a plain old cubic function like that. So this is c is equal to 0. Let me get a different color. Now, in green here, c would be equal to 1. All it did was shift the graph up 1, okay? But if you notice, they have the same shape everywhere. Meaning that, remember, derivative means slope. Okay? That means the slope is the same everywhere. This constant, whatever it is, does not affect the slope of the graph. Okay? So now we could have a third one that goes like this. This would be c is equal to -1. It shifted the graph down, and again, has the same slope everywhere. So when I take the derivative of this, the constant doesn't change the derivative. Okay? And we could do a third one. I got one more color. Let's see. This corresponds to c is equal to 2. We shifted it up 2 units. Okay? Again, the shape is the same. That means the slope is the same everywhere. The constant doesn't affect it. Now, again, we would have to be told a condition to come up with what c value goes there. And we will do that in examples later on. For now, we are just going to find the antiderivative of some functions and then just tack on a plus c. Okay, so let's do the next example. It's find the antiderivative. Find the antiderivative of the function, and we're going to do the most general, okay? The instructions on my notes says find the general antiderivative, save myself some room. So, A says f of x is equal to e to the x. Okay, we want to find the antiderivative, big F of x equals something. Can you think of a function, a function right here, such that when you take the derivative of this function, you get e to the x? This is a very simple one. It's simply e to the x. Now, when you take the derivative of e to the x, you do get e to the x ln e. Ln e is just 1, so it goes away. But don't forget the plus c. Okay? Most general antiderivative, got a plus c. Now let's look at the next one. Little f of x is equal to 6x squared. So we need to find the antiderivative. So this is a power rule again. Okay, we've got a power function here. So if we were to go backwards, remember, if we have a power function, we should have another power function down here. So I'm going to put an x. Since it is a power function, we would have to do the power rule on whatever this answer is to get this little f of x. So if I do the power rule on this, I do have to subtract 1 power. This power is a 2, so that means this power has to be a 3. Now, if I were to take the derivative of this, I would take the number, multiply it out front, and then I'd drop 1 power. So that's how I get the x squared, but there would be a 3 out front here. But there's a 6 out in front here. So if I were to take the derivative of this thing, the power would come out front, multiply it with what number to give me 6? What times 3 gives you 6? It'd be a 2 out there. So now, 3 times 2 is 6, and then I drop 1 power, I get x squared. And then don't forget your plus c. So all I did was go backwards in the power rule. We're going to talk more about that in a little bit more generally, give you a better idea of what you're doing, an easier way of thinking about it. So let's do the last example I have there. C, h of x is equal to negative cosine of x. So this is a trig derivative, or sorry, a trig function. So the antiderivative should probably be another trig function. Okay? So if you recall, sine of x, if we took the derivative of sine of x, we got cosine of x. If we took the derivative of cosine of x, we got negative sine of x. And if we took the derivative of negative sine of x, we got negative cosine of x. So this was doing derivatives. If you were to do antiderivatives, well, if you guess that it just goes backwards, I mean, that's a correct guess. It's just in reverse order, okay? So if you have negative cosine of x, the antiderivative of negative cosine of x is negative sine of x. The antiderivative of negative sine of x is cosine of x. The antiderivative of cosine of x is sine of x. And then it would just cycle back around, okay? So just based on looking at this, we could get the answer here. So the antiderivative of negative cosine of x is negative sine of x, and then don't forget your plus c. So you could always check yourself, okay? You could always see if you have the right answer. What you do is just take the derivative of your answer. H of x is equal to, well, the derivative of negative sine of x is negative cosine of x. The derivative of a constant is 0. So this right here, well, that equals my little h of x. That equals the starting problem. If you can do that, then your answer is correct. All right. You should go ahead and try the 2 problems I have there on my notes. It's find the antiderivative in the most general form of 4x cubed and also 1 over x. Now, be careful with the 1 over x one. It's a tricky one. All right, so now let's talk about the general antiderivative of f of x equals x to the n. Now, just recall the general derivative of this, f prime of x, is equal to n x to the n minus 1, okay? Let's think about this process right here and think about how we would go backwards, okay? Because once we figure out how to go backwards here to get this, we could use this and go backwards from here to get the antiderivative. think about the steps involved from using the power rule from here to here. What we did was we take the exponent, we multiplied it with the number out front. In our case, it's 1 here, so we just put it out front. And then we dropped 1 power. Okay, those were the steps. Now, if we go backwards from those steps, we will get this. So let's rewrite the steps. So going forward, one, multiply power with coefficient, and then 2, drop 1 power. That's if we're taking a derivative. So like I said, I think derivatives going forward, antiderivatives going backwards. Now, if we were to go backwards, so we have the derivative, let's get back to the original function. All we have to do is do these steps in reverse. Do them in exactly backwards. Okay? So, to find antiderivative of f of x equals x to the n, instead of dropping 1 power, going backwards is going up 1 power, raising 1 power. Raise 1 power. Going backwards from here, the opposite of multiply is divide. Divide the coefficient. So multiply power with coefficient. Instead, now you're going to divide the power. Oh, sorry, the coefficient by the power. So that's exactly backwards of taking a derivative. Okay? So let's see what we get when we apply it to this. If we were to do that to this, n to the x n minus 1, let's see if we get this real quick. Go up 1 power. So if I go up 1 power, I add 1 to the power, the minus 1 plus 1 cancel, x to the n. Then I divide the coefficient front by the power, divide by n divided by n is 1. You did get back with what you started with. So these rules do work. Let's go ahead and apply it to this one right here. So, x to the n, we start with that. We're going to raise 1 power. So I'm going to put a 1 out in front here, okay? There's a reason why I'm putting the 1 out front. So, 1, x to the n plus 1, so I go up 1 power, and then I got to divide this coefficient, that's why I put the 1 out there, divide the coefficient by the power, n plus 1. So now the antiderivative of little f of x is big F of x is equal to x to the n plus 1 divided by n plus 1 plus c. This is the most general antiderivative of a power function. Okay? Now, if you were to think about taking the derivative of this, let's go ahead and check. Let's check our work. If I take the derivative of this, and I get back this little f of x, I have the correct antiderivative. Let me organize this better. F of x is equal to x to the n. Big F of x is equal to x to the n plus 1 divided by n plus 1 plus c. Okay, let's take the derivative. F prime, big F prime of x is equal to, well, let's go ahead and do the power rule. I take the exponent, I multiply it by the coefficient out front. Let's say that's a 1 there. N plus 1 times 1 is n plus 1. X, n plus 1, I drop 1 power, so n plus 1 minus 1. Plus 1 minus 1 cancel, I just get an n. And then I still have an n plus 1 here. The derivative of a constant is 0. This n plus 1 and this n plus 1 cancel. I get back x to the n, which is exactly what I started with. So I indeed have the antiderivative. This is the most general antiderivative of a power function, just like we had a most general form of a derivative of a power function. All right, now there are some bullet points that go along with this. You got to be a little careful. So, big F of x equals x to the n plus 1 divided by n plus 1 plus c is the antiderivative. Save me some time, I was running out of room. Antiderivative of f of x equals x to the n. Now, this is valid for n greater than equal to 0. So, this is valid for any n greater than or equal to 0. That is because when n is a whole number, okay, when n is a whole number, it's a polynomial. Polynomial is defined everywhere, okay? Negative infinity to positive infinity. Now, if n is like a fractional number or a decimal number, it is still defined because nowhere will we have a division by 0, okay? So for instance, x to the 3/2 power or x to the 1.5, they're the same thing. This graph, it doesn't have any denominators. It's not a polynomial, but it's still defined on its domain, no problem, when n is greater than or equal to 0. Now, when n is equal to 0, that's really easy. It's equal to 1, okay? Now, here's another bullet. Probably the more important bullet than this one. If n is negative, but not n equals, or sorry, but let's see, what does it say? But n does not equal -1. That's very important. You should have noticed on the last example that I gave you guys to try, the function g of x was equal to 1 over x. Well, this is x to the -1st power, okay? That's what this bullet point is talking about right here. And if you looked at my solutions, the antiderivative of this, big G of x, is ln of x. Okay, the antiderivative of 1 over x, or x to the -1st power, is ln of x. That's why this condition right here is there. So if n is negative, but n does not equal -1, if it does equal -1, the antiderivative is ln of x. Okay? So, if n is negative, but not equal to -1, it is valid for any interval not containing 0. Okay? The reason being is because when this is a negative number, 0 is not in the domain. So let's go ahead and take a look at f of x is equal to x to the negative second power, okay? This is definitely n is negative. Now, it could be any negative number, negative 2.6, negative 3 halves, whatever you want, okay? Any negative, I just chose negative 2, make it easy. Now, if I were to rewrite this, this is the same thing as 1 over x squared, okay? The domain of this function here is everything from negative infinity to positive infinity except for 0. Anytime n is negative, you're going to run into this problem where it is not defined at 0, therefore you cannot find the integral on an interval containing 0. Okay? So, these are the cases. Like I said, this is the important one. You got to look out for the domain when n is negative. Also, you got to look out when the power is negative 1. Okay? So let's go ahead and do an example. It's find the most general antiderivative, 2x to the 7th minus 4x to the 1/5 plus x to the negative 1st plus 3 divided by x squared. So it's a bunch of power rules. Like I said at the beginning of this video, we're going to learn how to undo the power rule. We're also going to learn how to undo the chain rule. Okay? So we're learning how to undo the power rule right now. So if we follow the general rules for taking an antiderivative of power functions, big F of x is equal to, now I am going to rewrite this one as 3x to the negative second, okay? 3x to the negative second. So what the general power rule, antiderivative power rule says, you go up one power and then divide by that power. So x to the, go up one power, that's at a 7, so I'm at an 8. And then I'm going to take the coefficient and I'm going to divide it by this power, 8. We'll simplify in the next step. Minus right there. Now, I'm still going to have a power function, x to the 1/5. Even though it's a fraction, it's positive, you still follow the same rule. You go up one power. 1/5 plus 1 is 6/5. You could turn it into a decimal. This is a nice decimal, 0.2. 0.2 plus 1 is 1.2. You have x to the 1.2 there. Now, you take the coefficient and you're going to divide it by this power, 6 over 5. Plus, now don't go up one power. If you go up one power, you're going to get x to the 0. Divide by that power divided by 0. That should tell you that you have a problem there. You were not supposed to anti-differentiate x to the negative first power because of that bullet point right there. When x is negative, or sorry, when n is negative, but not n is equal to negative 1, if it's equal to negative 1, you run into that problem with the division by 0. Okay, that should be your alert. It should not be the power rule. In fact, it should be ln of x. Now, remember, ignore this. I rewrote that as 3x to the negative second. Now, still, undo the power rule. Even though it's a negative here, go up one power. Add 1 to this power. You get x to the negative 1. And then you're going to divide, so there's a plus here, 3 divided by this power, negative 1. So that's what I did here for the power rule. I went up one power, divided by that power. 1 up one power, divided by that power. this was a special case where you get natural log, go up 1 power, negative 2 plus 1 is negative 1, and then I divided by that power. So, plus c. Don't forget your plus c. Now, to simplify, this is 1/4 x to the 8th minus, now if you were to plug that into a calculator, let's see, 10 over 3. I think you get 10 over 3. I just did that really quick. Plus ln of x, and this turns into a minus. You could rewrite it as 3 over x plus c. Now again, you could always check your work. Take the derivative of this, and if you take the derivative, you get back your original problem, you have the correct answer. So now, you can pause the video. There's a problem for you to try. So go ahead, take some time, do that problem, and then check my solution online. See how you did. But now there is a way of doing antiderivatives. Again, if you know your derivatives really well, just going backwards is pretty easy, okay? Now, they do have tables of antiderivatives. If you notice in my notes, I just took this out of the book. It has a whole list of them, okay? The first one says c times the function of x is equal to, all this is saying is if you have a constant that you could factor out of your function, then when you find the antiderivative, it's the same thing as that constant times the antiderivative. The next one says that if you have two functions and you're adding them, all you do is find the antiderivative of the first one, add it to the antiderivative of the second one, okay? So I'm not going to write up all these on the board. You have all these. Now, if you notice, it says the antiderivative of 1 over x. It's ln of absolute value of x. The absolute value bars are there to ensure that the x is positive. Remember, ln, you cannot plug negative numbers into there, otherwise you're going to get complex numbers. So the absolute value bars are there to ensure that you will always have positive numbers there. Now there's a whole bunch of them. I would give a look through them. If you go back to chapter 3 and look at a table of derivatives, if you go backwards, those are also the antiderivatives. It may have a bigger list than what you see here. Okay?